to start. It's 3:30. Welcome to our Friday's control seminar. And today, it's first of all, I want to acknowledge the sponsors for the seminar: Toyota, Seagate, Mitsubishi Electric, Qualcomm, and MathWorks. And today, I have a distinct pleasure to introduce Professor Gabor Orosz, who is a professor in mechanical engineering department. And he's of course one of our own, so needs no introduction. So I'll cut it short, but I will mention that his research interests are on linear dynamics and control, time delay systems, machine learning, and data-driven systems application to connected and automated vehicles, traffic flow, and biological networks. And recently there was a very nice book coming out, Dynamics and Control of Connected Vehicles, Springer book, and he's the lead author of that book. And so with that, I'll give you the podium.
Thank you very much, Ilya. So, well, welcome everyone, and I will try to entertain you in the next 1 hour or so. So hopefully it was worth to come to the seminar. So I will talk about vehicles and control barrier functions. So these are two topics which my group are very much interested in. This is indeed a bigger effort. So here are a couple of faces who kind of get involved in this. So Ilesh and Yuchen, they are in my group. So they are the kind of CBF guys in my group these days. And then we are collaborating also with Professor Yakovlevsky's group. In particular, in the last year and a half, we have been working with Xiao quite a bit. And there is a collaboration with Toyota Research Institute. So these are the main folks who we work with, and I will show you the capabilities they have. It's really amazing. And then at the bottom row, I mentioned a couple of collaborators from other universities. So if you ever read a CBF article, there's no way that you haven't seen Aaron Ames' name, right? So it has to be there. Tamás actually was a postdoc here in Michigan with me, and then he also spent some time at Caltech with Aaron, and now he's at Wichita State University. And Professor Dénes Takács is in Budapest, and his insights on vehicle modeling and dynamics is very much valuable. So let me try to show what we are after. Okay, so first of all, if you read the news, let's say 5, 6, 7 years ago, maybe at that time you were not even in grad school, I hope not, then basically you see that by now we don't drive, right? We have automated vehicles, we press the button and it takes us from A to B. I mean, CEOs of major companies went on stage and said, in 3 years, we're gonna manufacture level 4 AVs, level 5 AVs, right? Already 7, 8 years ago, this was there, right? That became a little slower, right? I'm not saying it's not happening, right? Clearly, there are a lot of nice deployments. Just heard Google is actually going to New York City. That will be a nice quest, actually. But it's definitely going much slower than we expected. And one of the reasons is that there are just so many corner cases which they have to cover, okay? And there are different ways people are thinking about it, how it can be done. Should we, boost up the AI and eventually it's going to be so intelligent that it's able to handle everything? Should we do it in a classical way and so on? So today I'm going to show you one way to kind of do this quest and try to make these vehicles safe, despite the fact that we may not have the most performant AI on board. Okay. And then TRI in particular, they worked a lot on pushing the vehicle to the limit. I will show a couple of videos about it. They were interested in how to make it happen, and they used very sophisticated control techniques. In particular, they used a lot of nonlinear MPC. If you ever worked on that, you know how hard it can be, right? Because maybe it doesn't converge. Maybe I have to linearize. I linearize on what? There are a lot of questions there, and often the computation becomes quite challenging. And what we're really interested in is having algorithms which can actually guide humans, or as a matter of fact, also guide or guard AI-driven algorithms, such that we can kind of put it on the top of it, and we can make sure that well, we say guarantee safety, because in our framework we will say guarantee, but in a kind of broader sense, at least improve the safety of those vehicles. Okay, so that's the main goal. Okay. Anytime you have any questions, you can jump in. But I will get our hands dirty very quickly. So I will talk a little bit about the techniques we're going to use today. Okay, so in particular, we like control-affine systems. They are really nice. As a matter of fact, luckily, mechanics often gives us control-affine systems because forces are linear, right? So since Newton, we know that we can add together forces, right? So we often get this form. And when we talk about safety, we're typically interested in a part in a state space, okay? So you have to define the state space. You need to figure out what states you are interested in. And then when we talk about safety, we typically think about forward invariance, right? So in this particular case, if I start in this green ellipse with my initial condition x0, then I'm going to stay in that green ellipse in all the time, because all the xt should stay there, right? And I'm not specifying what must happen in or not happen in the green ellipse. I just want to stay in that. So if I'm able to achieve this, then I can achieve safety in my definitions. Okay. So the tool we use is called a barrier function or control barrier function. The idea is that, if we are in the set, we're safe. If we are outside of that, we are unsafe. So if we define a scalar function, which is positive inside and negative outside, then we can characterize safety. And we can also somewhat characterize how safe we are. Okay, so for example, in this case of this ellipse, you can build this dome. Okay, so it's just a scalar valued function. And then we want to make sure that this function stays positive. Okay, so then we can turn this idea of staying in a set into making something positive, right? Going something which is potentially high dimensional, something which is just a single dimension. Okay, and the advantage of this, that we can actually have a nice condition for it. So I framed it here. This is what people often call the barrier certificate. Okay, so if that is true, then we know we are able to maintain the safety, and we can use it as a constraint on an optimization problem. Okay, so this is a instantaneous optimization problem, which is basically saying that I'm trying to see what is the deviation of my control input from my desired one. Okay, and then I just take the minimum. So if there is no constraint, then I just use the desired controller. Okay, where does the desired controller come from? It can come from the human. It can come from the AI. It can come from some other control algorithms. Okay, in general, this method doesn't care about it. It allows you to do the control on the top of it. Okay, so that's why we often refer to it as a safety filter. Okay, so it's something which is the control input which is fed into your system is filtered, and that what comes out of it is filtered is now gonna guarantee safety. Okay, so the nice thing about this algorithm, it's very simple. Often you can actually solve it analytically. Okay, so for example, I'm showing you the analytical solution for a single input case. Even for multi-input, it's not much more complicated. Okay, so you can see that basically what happens is that depending on this derivative being negative, 0, or positive, okay, I have 3 different algorithms. In particular, when this is equal to 0, and this will come up later, then I'm using my nominal controller. When it's negative, I'm just taking the minimum between my desired controller and the safety controller, and I'm taking the maximum when this is positive. That's simple. Okay, this is 3 lines of code, or 4 if you wish. Okay? Nice thing is that indeed this safety critical controller is also just a very simple expression. Okay, you can get it analytically, and you can run it on any hardware basically as fast as you want. Okay, so that's kind of the advantage of this methodology. Then it's very lightweight, and it can be put on pretty much on the top of anything. Okay, so if that's roughly clear, then let's try to put it on a vehicle. And turns out it's not that simple as we think. But we started with the simplest possible model we could imagine for a vehicle, and this is what we refer as the kinematic bicycle model. So in this case, we imagine that the rear wheel is kind of rigid, right? So there are no side slip on the rear, and the front wheel is also rigid. There's no side slip at the front. So this model can be described by only 3 coordinates. Okay, so the position of a particular point of the body. So in this case, I chose the rear wheel center because that keeps the model simple. And then I'm going to also use the yaw angle to give us the orientation. Okay, so this is going to tell us where is the vehicle in space and what is the orientation. And as a matter of fact, I'm only going to use in this case two of these three states because I want to keep this vehicle in the lane. Okay, so I'm only going to use the yaw angle and the lateral error. So this gives us a control-affine system. So we are in the game, right? There are only two states. This system is nonlinear, right? We have a sign C here. And even if it wasn't, through this CBF, we will make it nonlinear. Okay, so even if you try to put the CBF on the top of a linear system, typically makes it nonlinear. Okay, now I talked a lot about this like nominal controller, which can come from different places. So we came up with the probably simplest possible one, and this is something which actually many vehicles on the market are using when they do lane keeping. So they basically measure the lateral error, so how far from the lane center, so that's the YR. They measure the yaw angle, and they basically feed them back with a state feedback proportional controller. Okay. Certainly, you can do much more complicated things, but this is really something which, if you took linear systems, then they talk about these kind of feedback, and then you know how to design it. You can place the poles and so on. Okay. Our goal was not to kind of design this controller to be nice. This is really just there so we can put the CBF on the top of it. Okay. Now, how do we do the CBF? Well, we need to define safety. And then you can see on the right, I put the vehicle in the lane in 4 different configurations. And those four different configurations are particular because that's exactly when the corner of the vehicle is just sticking out of the lane. Okay, so these are the kind of border cases. And if you turn it into state space, then you would get this, what I call the exact safe set, or this gray kind of parallelogram looking thing. It's not exactly a parallelogram. It's going to be a little bent. So we quickly made a parallelogram fit, which is nicer, right? The polygon is always is more beautiful. And then as a matter of fact, eventually we put an ellipse into it. So we became a little more conservative because we want differentiability. So those corners are typically difficult. CBF, we have to take derivatives. Now, if you want to have another shape to fill it out, you can do that. You can do it with a higher norm, and then you will be able to do that. Okay, so that's possible, but today I'm only going to show you the ellipse. Okay, so in particular, the 4 sides here are corresponding to these 4 different corner cases, right? And then our goal is to stay in this green ellipse. Okay, so as we discussed before, we build a dome, right? That is positive on the ellipse and it's negative outside of the ellipse. And so this actually has a very nice analytical form. This is you just write it as a second order function, right? You can see it here. And you can calculate all these coefficients. They are just numbers, right? They depend on the geometry of the vehicle, like what is the wheelbase, what is the overhang in the front, what is the overhang in the on the back. So if you have to do it for a school bus in Michigan, those have really large overhang in the rear. You have to take that into account. If you're doing it for a short SUV, then probably that's not a big issue. Okay. And again, nice thing is that we still have this control-affine system. And in this particular case, you can again calculate this safe controller in a closed form. Okay, so this is very nice. You see, it's basically a second order polynomial divided by a linear thing, right? And it's very easy to implement in any hardware. Okay, so if I put this together with my nominal controller, then I can do this safety critical control, which we discussed. And then this is the whole system. Okay, so now this gives us a closed loop system, which we can analyze. Okay, and that's typically a good idea to do that, right? So, you should not stop and it's like, oh, according to Aeronames's theorem, this is a proven and safe controller. That's it, right? You should take a look at it, especially if you want to do experiments, right? If you want to go from theory to experiments, you typically need to do some kind of either numerical or analytical analysis in the middle to make sure that that thing really works how you want it to work, okay? So let me show you, for example, a simulation, which we did. So this is a very simple scenario, okay? So now we can see the green ellipse, and on the left, I'm showing you the nominal controller. So this is a stable controller. As a matter of fact, for any choice of those 2 gains, this system is going to be stable, okay? But as you can see, in terms of safety, it doesn't work very well, right? The red trajectory in particular emphasized shoots out of the ellipse and eventually comes back, okay? So that shows that stability may not be enough, right? You may be stable, but you may still die, okay? So you have to be also ensure the safety of the system. As you can see on the right, this is where we turn on the CBF. As a matter of fact, when we are in the yellow region, there is no CBF turned on. We're just using a nominal controller, okay? It doesn't compromise safety. When we switch to the blue areas, okay, according to those switching rows which I showed you, then we change the flow and we divert it in a way that it comes back, right? So you can see, for example, for the green trajectory, it enters to this domain where the system has to turn on the safety critical control, and then eventually it comes back, and it also stable, right? So it goes back to the lane center, okay? So we kind of want to make sure that this kind of behavior happens, and it doesn't just happen in our simulations, but it also happens in experiments, okay? So luckily, our collaborator, TRI, has a very nice platform. This is our kind of working horse. So this vehicle is very capable without using all the capabilities. It has a 4 hub motors, so all the wheels are independently driven, okay? It has front steering and rear steering as well, so you can steer the front and the rear, okay? So you can do crab walk if you want, okay? And then it's indeed fully electric, so it's very easy to accelerate and so on, right? So that's a nice nice platform. And this is what we use. Now, of course, we needed to initialize the system such that we can match that simulation which I showed to you. The initial phase, we just ran up, and then eventually we turn it on. And the nice thing was that at that point, we can just draw our own lanes, right? So we didn't actually have to do it physically, didn't have to do it with the sensors. The vehicle just believed that's where the lanes are. Okay, so let me show you how did it work, okay? So this is the drone footage, okay? So at the beginning, these lanes were not there, but quickly at the initial condition, they are drawn. And you can see in particular at the beginning, there is some difference, right? So the nominal controller, it leaves the lane, okay? And then eventually it decays in its motion, but it's definitely not safe, right? When you look at the safety filter on the top of it, then you see that there are those blue trajectory parts, and that's the time when the CBF kicks in, okay? Otherwise, the system is just using this simple nominal controller, okay? So it's a very simple switching rules between them, okay? If you look at it in state space, this is how it looks like. So this is the ellipse where we want to be at, okay? And as you see, we didn't exactly stay in the ellipse. Obviously, there are modeling errors here, right? We are using a kinematic bicycle model, but definitely we didn't shoot that far as the nominal controller would have done, okay? So you can see here that we switch, okay? And when you reach this boundary, we switch back, and eventually we settle down. And you can also see the input. So here is the steering angle, okay? So this is the angle at the road, okay? So we call it the road wheel angle. So that's about 10 degrees. Typically, you multiply it with 15, so that means about a 150-degree turn of your steering wheel, okay? So that's what the vehicle is doing. So it's not something crazy, okay? It's definitely doable. We run it at different speeds. So for example, here you can see the experiments ran for like 6 meters per second, 8 meters per second, 10 meters per second. These are relatively low speeds, right? So even 10 meters per second is about like, I don't know, 22 miles per hour or something like that. That's when I say real driving really starts. And you can see the red trajectory, which is without the filter, it goes over the moon, right? It's really doing pretty bad. But the safety filter is keeping us really close. It doesn't exactly able to keep us in the ellipse, but it was really close. And indeed, as the speed is increasing, the error gets larger, right? So it's clearly something we are missing there. The kinematic bicycle model is maybe not exactly what happens in the model, okay? So we got excited because we were like, whoa, okay, so it works for this simple controller. What if we try to put it on the top of a human? Okay, so that was the real test because we have no idea how the human drives. He does what he wants to do, okay? So whether we can stay in the lane, that was kind of a good question. So it surprisingly worked very well. So what you see here again, wherever you see blue, then the CBF intervenes. Whenever you see yellow, it allows what the driver does. And so you can also see in the steering angle the red things which the driver is asking, right? But he's not getting because it would compromise safety. So you can see it basically tries to ram to the walls, right, to the lane boundaries, but the CVF actually intervenes and it hands it back. In this case, actually, we stayed in the ellipse. And one reason is that our initial condition was actually less abrupt, right? So in the previous example, we deliberately put the vehicle in a really weird kind of high angle scenario in the lane. And in this case, we started somewhere in the lane, in the center of the lane, and then the driver was trying to kind of pull it out or not, okay? And this actually worked even for higher speeds. So you can see that I'm showing it for 6, 8, and 10 meters per second. So this worked more robustly, okay? So the way kind of I like to show it is this is when the vehicle is coming toward you. As you can see, there are no drawn lane marks. So the driver just kind of feels out where the lane is. And then it's trying to get the car out of the lane, but the CVF doesn't allow it, right? And at the end, he's actually getting pretty wild. And this is when I learned that, you know, be careful when you go to California in November. It could be really, really cold. It was about 5 degrees centigrade. Sitting on that car was super cold, right? But it was super fun, I have to tell you. Okay, so hopefully this demonstrates that these techniques are useful and they can be put on real hardware relatively quick. So I have to tell you, this was the first experiment in my life. When we went there, we put the code on the vehicle and it worked the first time. Okay? First time worked. That's very rarely happens, right? That's not typically how we do experiments, okay? So it was very robust and we were very happy about the results, of course. Okay. So what are we missing here? Well, quite a lot, right? So, I mean, that kinematic bicycle model which we use for our design, this is a model-based design after all. Actually, this is an important point. Safety must be model-based, okay? Whether that model comes from, it could come from first principles, it could come from some learning, but there must be a model there. Otherwise, you won't be able to do safety, okay? So the idea that you're gonna go into a ChatGTP and tune a couple of gains there and make it safe, forget about it, right? It must be some model there. Again, it can be database model, right? But it must be a model to make it clear, okay? So clearly our model here had some lackings, right? Even for lower speeds, we could see that it was not perfect, okay? What we are really missing is what we call the tire dynamics in vehicle dynamics, okay? So as a matter of fact, we don't have rigid wheels, right? We have elastic tires and we use them to our advantage a lot, right? But what they actually cause is that when I turn my steering wheel, there will be some elastic deformations there. So the kind of the direction I want to go to, I'm not really exactly gonna go to that, okay? So I will elaborate on it a little bit, okay? So now this actually gives us a lot of interesting abilities, right? So we have kind of more freedom to play with, okay? And there are people who do that. So for example, these are two guys who have some fun, okay? The two particular motions are actually important what they are doing. So one of them is called the donut, okay? The donut is when you turn your steering wheel to the left and you turn to the left, okay? And then you also have the drifting, okay? The drifting is when you do the opposite. Interestingly, you turn your steering wheel to the right and the vehicle is still turning to the left, okay? So that kind of keep people puzzled, you know, how this can work and, you know, how can we do that? And skilled drivers have been able to do it. If you watch movies, you know, typically the first car chase, you know, there's a lot of drifting happening. One good one is actually the latest James Bond movie in which James Bond dies. I'm sorry for the spoiler. I messed up, right? But anyway, it has been out there for 5 years or so. So there is a very nice car chase at the beginning. You should look at that. Okay, so we can see there is, you know, additional degree of freedom here to play with. Why is this so hard? Okay, well, a few years ago, this guy, whose name is Richard Hammond, he tried to actually learn, you know, to drift. Okay, so he went to France, I think, and then he asked a professional driver to teach him to drift. And so this is Hammond trying to learn the drift. Okay, you can see there's a lot of movements on the steering wheel. Not quite what you want. Okay, so in general, you kind of want to have this steady motion going on the circle. Well, he's not doing that. Okay, and so that this master of drifting is trying to teach him, he keeps failing, right? Eventually, actually, he got it right. But as you can see, the driver instructor was not very happy for quite a while. Okay, so why is this so hard? It's because even though these motions exist, they are actually steady states of our system. They are unstable steady states. We need to stabilize them, okay? And skilled drivers know how to do it. Let's try to do it in a control engineer's fashion, okay? So now, who's playing, right, the video? Exactly. I have too many screens here, I'm sorry. Yeah, I have like 3 screens and I don't know which one is which, so I'm a little confused. Okay, so in order to do this, as I mentioned, we need a better model, okay? We can't have those tires just rigid anymore, okay? So that means we have more states, okay? So in this particular case, we're actually going to have 6 states. So we need to have the position of the vehicle. We need to know the position of a point. In this case, I chose the center of mass, C, okay? I need to know the orientation, so that's the C. And now I also have velocities. So I have a velocity component is the longitudinal velocity and the lateral velocity. So they're actually done in the coordinate system of the vehicle. And we also have the yaw rate, this omega. And now we have 2 inputs. As a matter of fact, we are playing with the torque at the rear wheel, and we're also playing with the steering angle, okay? And of course, it's a rear-wheel drive vehicle, and that's when you can have a lot of fun. So I'm kind of putting the torque all on the rear wheel and nothing on the front wheel, okay? You can play more, but this is what we're gonna do today. And then you can also see on the bottom left, there are these 2 new quantities, this alpha R and alpha F. So these are what we call as slip angles, right? So you see now this VR velocity, it's not aligned with the vehicle body and the wheel, okay? It actually has an angle here, okay? And also you can see it on the front, right? So there is a angle between them, okay? And that's how we can actually calculate these forces, right? This Fy and Fy force here, which are the so-called lateral forces, okay? So now these become active forces, and we will calculate them from the tire deformation, okay? When we had it in the kinematic model, they are actually constraints. They are non-Holomic constraints, which we can use, okay? So indeed, our model gets more complicated. The kinematics itself is still 3 equations, right? So they describe how the center of mass, in this case, velocity components and the yaw rates are put together. And the dynamical equations, as a matter of fact, in this simple case, you can just get from Newton's second law, okay? So you basically have 1 equation for the longitudinal dynamics, 1 for the lateral dynamics, and 1 for the rotation, okay? This is relatively simple in this case. Only one thing is that I'm writing these equations in the body fixed frame, okay? So this is actually the velocity in the body fixed frame of the vehicle, and this is also the velocity component in the body fixed frame of the vehicle. And that's a nice thing to do in these systems. We also use it in aerospace systems as well, right? Because these are quantities we can often measure on board, while the X, Y, and Z, we have to have some ground free coordinate system to measure. As a matter of fact, for TRI, the way they do it is that they have RTK GPS on the vehicle, right? So then they can measure basically the position very accurately, and they can also measure the orientation. Okay, so that's the way we kind of eliminate any need of sensors like lidars, radars, camera, which would make our life quite complicated. Okay, so one thing I want to mention that if you ever go to a vehicle dynamics conference, then people often don't talk about the lateral velocity. They like to talk about the body slip angle. So this beta, okay, here, which is basically calculated from the lateral and longitudinal components, okay? So this equation is often rewritten in those coordinates. They got a little more complicated, but again, vehicle dynamics people like it, so I'm gonna use it today. So we can use the magnitude of the velocity of the center of mass, and we can use this body slip angle, okay? These are equivalent to each other, so there's no difference. Important thing is now we have 6 states, and definitely previously we had actually 3 or actually 2, right? That will make our life more complicated. Okay. Now, what I missed here is the tire itself. Okay, so I mentioned that, we need to have some tire model. That's a very large field on its own. Okay, so for example, if you type tire dynamics into Google, probably the first thing comes up is a book by Hans Pacheca. It's about 600 pages. Okay, and all the tire wisdom of 50 years are in it, right? So it's not that trivial to understand what happens. We need something which is high fidelity enough, but at the same time, it's simple enough. Okay, so we went back quite a bit in history. One of the earliest models, it's called the Fiala model. It was written in 1954, okay? So Ernst Fiala was actually someone who introduced the Volkswagen Golf, okay? So he's a guy he's still alive, he's about 98, okay? And that was in his PhD thesis. So that's some work, right? If in your thesis, 54 was how many years ago? 71? Right? So think about your PhD thesis, write something which we're going to use in 71 years from now. I think that's impact, okay? It's a relatively simple model, and that's why it's actually very useful. So what it does, it basically tells us what is this lateral force as a function of the slip angle, okay? There are many approximations, of course, made, but there are a couple of important quantities. So one is that we have something called a cornering stiffness. So that's actually in the linear regime of the tire here. Okay, so the gradient there is what we call the cornering stiffness. And then we also have some higher order terms. Okay, and you can also see it's not that trivial. Eventually what happens is there's a switch here. So once we reach this sliding angle, right, then we start to slide, and then basically we have no control of the vehicle. Getting into this regime is really dangerous, okay? You don't want to do that because basically you can just spin out and you can't do anything about it, okay? Another additional thing is that we also factor in the longitudinal force. So we omit the longitudinal deformation of the tire, but we know that we need some force to kind of push that vehicle forward, and that is kind of taken out of the available lateral force, okay? And we drive it with a torque in the rear. There's no torque at the front. And then the weight is just static weight distribution, okay? So this used to be a big headache for the vehicle industry because, well, you probably heard about the 50-50 weight ratio, okay? But it was very difficult to achieve it by design because engine was at the front. It's very heavy, right? So engineers spend a lot of effort of kind of shifting weight here and there, making sure everyone is feeling comfortable and so on. That's not a problem now with electrification. You have a big battery on the bottom. There's no per se engine anymore. There are those motors, but they are very small weight. So we are very close to 50-50 these days. That's not a problem anymore. Okay. One thing I want to mention here in this model is that there's a very interesting nonlinearity here. Okay. So you see, it's basically the powers of tangent alpha, right? So first is tangent alpha, it's the second power of tangent alpha, and the third power. But if you look at the second term, that's actually, there's an absolute value there. That's a really nasty nonlinearity. You actually can't see it on the graph because it's related to the second derivative, right? So it's a smooth function, but it can cause a lot of trouble and it can cause a lot of interesting dynamical phenomena, okay? This is not a proper Taylor expansion, okay? So you can get into some interesting phenomena out of that. Okay, so now we have a vehicle model. We have 6 states, right? We have the tire. We can calculate those forces. We put them all together and let's see what happens. Okay, so first, let's take a look at the steady states. So this is a tool which we often use in my group. It's called bifurcation analysis. So what you can actually do is you can take a parameter like the driving torque here, which is just constant. Okay, so imagine that I'm putting a constant torque on it. And let's fit my steering angle just to 10 degrees, okay? And then I increase this driving torque and I find the steady state solutions of that system, okay? So what you see on the right, I'm plotting the longitudinal velocity. If I start to add more torque in the rear, right, I'm getting more velocity, right? So my steady state velocity is increasing. up to a point, but here, close to this peak, I'm losing stability and it becomes unstable, okay? So if you look at, for example, this solution A and solution B, this is for the same longitudinal velocity. A would be this kind of nice weekend driving, right, which you would do in the weekend. But then this B is this very interesting solution. It's very narrow, okay, for the same longitudinal velocity. It's actually almost spinning on the spot. That's the donut, okay? I'm turning my steering wheel and I'm doing it. Interestingly, there is another solution coming here, and this is what we refer as drifting. You have to have a powerful enough vehicle to have that, right? So above a certain Newton meter, it just comes in. And what it does is actually, it turns the other way, as we discussed, right? So drifting is turning the opposite direction, okay? So you can find these states here. And as a matter of fact, you can also see that two of them are unstable and one of them is stable, okay? So for the same torque, you can actually have all these three. Now, what if I want to stabilize it? Well, this community has zillions of techniques for that, right? What we typically do is we linearize the system around it and we design a controller. And then, of course, we test how well that controller works, say, on the nonlinear level. But of course, you can do it in many different ways. You can use the Lyapunov techniques. What we did was something very simple, as I mentioned. We know where the steady state is. And as a matter of fact, we only have to focus on 3 of the states here, right? So we only focus on the velocity component, and we focus on the yaw rate. And we don't care about, at this point, the position and the angle, okay? And then we put constant steering angle, constant torque. And then this is standard linear systems. Who is teaching linear systems? Jeff, are you?
No, not this one.
No, it's not your fault then. But anyways, but but definitely you guys do linearization, right? In that. All right. So then you got this AB system, and then you can shoot it with something very simple like an ALQR. Okay, so that's what we did. We wrote an ALQR on it. It's a linear control technique. You solve your, it's an infinite horizon ALQR, right? You got your Riccati equation, you got your state feedback. Okay, so this is a linear feedback around your equilibrium, and it works very nicely. Surprisingly, you can actually stabilize drifting pretty much anywhere you start from state space. So it's not proven to be globally stable, but practically it is. Okay, why this works so nicely? Because we had a good model. So if you try to do the same thing on a kinematic bicycle model, it would not work. Okay, you have to have a high fidelity model enough, which is simple enough, of course, that I can use this technique, but actually it works nicely. Okay, so this is how it looks. For example, you can see the trajectory on the top, on the right. So I start from the middle of this diagram. I increase the speed. I overshoot a little bit. That's okay. Okay, I just want to stabilize. And this is the lateral velocity. This is the yaw rate. This is probably the most interesting thing, is that what is what you're doing with the steering angle. Okay, so the way actually you got often into the drift motion, then you kind of turn your system into close to a donut, right? So you basically turn your steering wheel a lot, then you kind of get the back of the vehicle to break away, and then you turn around your steering wheel and you stabilize, okay? And it does it automatically, right? So this kind of back and forth swing, we didn't code it in. It's just the controller did it very nicely, okay? It's a very robust thing. As a matter of fact, Professor Chris Gerdes, who is was a professor at Stanford University, they actually did it with this kind of old-looking vehicle. Did anyone watch Back to the Future here? That's in the past, as you know, right? So that's already happened. But that's actually a DeLorean, which they took out the engine and everything. That also didn't work so much anyway. It was a bad engine. But then they basically did this controller. And you could see that they could actually even switch between different motions, right? So they could go from like counterclockwise drifting to clockwise drifting. Okay, so it was really nice. It's about 6 years ago they came up with it. And since then, there's a lot of kind of people trailing it. So we just came back from a conference in Shanghai a couple of weeks ago. Everyone was drifting, okay? Everyone was doing that, right? Why? because A, it's, as you can see, you can do it relatively robustly. B, because now we have electric drives and it's much easier to do it. If you try to do it with an internal combustion engine, that's much, much harder, okay? So now if you, for example, you go to YouTube, then I step out here, then you can look at this video. I couldn't insert it into the PPT, but I will show you. So this is the SU7 drifting, okay? A lot of smoke. So he has a handbrake, right? So he can actually initiate the drift that way. Okay, you can download it. It's a cool video, okay? So the point with this, we obviously missed something here. Oopsie, I think I closed my slides. I'm sorry about it. 1 second. Go back. Yeah, so we were here. We missed something because indeed, there is a lot of motion in the longitudinal direction, okay? The smoke comes from somewhere, okay? You're burning a lot of tire. And the model we had actually didn't really model it very well. The price we pay for that I mentioned, it's relatively easy to stabilize drifting. It's actually very hard to stabilize donuts, okay? So to do it in a stable and controlled way is very difficult. We actually need a better vehicle model for that. We need to count for the wheel speed dynamics, okay? The wheel speed is not gonna match the vehicle speed, right, when you're burning your tires, right? So that's also important. And as a matter of fact, if you do that, then the same LQR technique with a little bit more states, so this is a 5 degree of freedom model, so eventually we will deal with 5 states, you can actually do it. So you can, we didn't do it in real life, but you can do it at least in simulation. You can see we are actually going from counterclockwise drifting to clockwise drifting, from drifting to donut, from counterclockwise donut to clockwise donut. And the advantage of this is that, you know, even at the transients between, say, the 2 donuts, right? Those are the little science ones. You can see even the transients has a very small radius, okay? So this means high maneuverability. If I'm able to control a motion like this, I can turn that vehicle on the spot really, really quickly, okay? So great. So now we can do it in an automated vehicle. But I started this whole presentation is that where are the AV4s, right? So, you know, it doesn't look like that we're going to sit in one of those soon as our own personal vehicle. Also, you know, I don't think that Google is going to drift in New York City, right? That's probably not likely, okay? So what we want is that these capabilities, which these controllers are able to do, we would like to make sure that humans can have it or AI-driven vehicles can have it. They don't want them to drift all the time, but we want the vehicle to be kept safe, okay? So to circle back, you know, we started with CBFs. Now we can do the same thing in the higher dimensional state space. In particular, here we care about this slide slip angle, which I mentioned is related to the ratio between the lateral and the longitudinal velocity, and then also the yaw rate. Okay, so actually, John Subashits, who was previously a PhD student at Stanford, he figured out, you know, that we can actually find these limits of what the vehicle can do essentially as null lines. So what he did was he basically said, oh yeah, let's fix the velocity, the longitudinal velocity, and then let's turn the steering wheel to the max, and let's see what is that limit, okay? Because certainly I can't do more than that, right? I can't turn the steering wheel more. So those are actually those black and dashed black lines. And then again, to keep it simple, we're gonna put an ellipse into the middle. Okay, so again, now we deal with 3 states, as a matter of fact, which we care about. We don't care about the kinematics at this point, and 2 inputs. Okay, so same scenario works as before. We can actually construct a safety filter. There are little caveats here. So now we have more than 1 input. Okay, so it's a little harder to solve this optimization problem, but it's possible. It's probably 2 more lines in your code, so it's not a big deal. Okay. The other thing is that you can see this gamma here. What it is that a way I'm calculating is that I have to weight my coast function, because I'm using here the delta, the steering angle, and also the torque, right? They are even different units, right? So that takes a little bit of tuning to make sure that you are doing it in the right way, okay? So if you are able to do it, then you should be able to keep the vehicle in this ellipse, i.e. you are able to keep it safe, not spinning away, okay? However, it gets a little more complex, okay? So as a matter of fact, one issue is the input is our steering angle, okay? So that actually is not control affine. So the problem is it comes through the slip angle and it gets crazy nonlinear. So all that beautiful theorems which you can prove, you know, for control affine systems, they go out of the window, okay? Well, luckily, there is something called the dynamic extension, which many of you probably have dealt with this before. You know, when someone says, hey, I can't control this signal, but I can control the rate of it, right? That's a dynamic extension. The same thing you happen here, you actually control the steering rate and you control the torque rate, and you got 2 more dimensions to deal with, right? So we are back to 5 as a matter of fact, still not huge, okay? The issue is that in this case, when you try to do the CBF, then the derivative doesn't contain U, okay? So actually you can't synthesize a controller. But again, there is a solution for that. We call it higher order CBF. So what we basically do is we assign a new CBF, okay? And what you're basically solving is this optimization problem, okay? So now you have the coast function, which is kind of same as before. And instead of a first order constraint for the U, you have a second order constraint for the U, okay? So it's not that difficult to do. Indeed, you have a few more parameters to play with. You do need some, right? So if you ever try to run an experiment, you know that no parameter is not a good idea. You have to be able to tune something because it's then I can actually play with the performance, okay? So it works in simulation very nicely. As you can see here, there are a couple of times when with different strategies, basically the vehicle is driven to the limit, okay? And as you see the trajectory, as it goes close to that red ellipse, right? Then the color of the trajectory changes. Both in terms of the torque and both in terms of the steering, right? So for example, if you see the one on the right, what happens here is this is actually a transition from a clockwise drift to a counterclockwise drift. So it's probably the hardest thing to do. And as you can see that the blue part is when you're kicking in, right? Essentially, you can see you're taking away steering, right? So that's why it kind of becomes negative. And you're also taking away a little bit of torque, okay? And you do it in a smart way, so the vehicle is still staying inside this in this ellipse, okay? And of course, the real test is, does it work on a human? And luckily, it does, okay? So my colleagues had a lot of fun with this, okay? They have been drifting for a long time. And as we can see here is on these trajectories, so it's again showing how much steering and how much torque you are taking away or adding to the system. So that's the color trajectories. When you're getting close to those drifting and donut states, right? Those are the ones in the corners, then the system starts to kick in, okay? It doesn't just try to stabilize these. Actually, it doesn't know what you want to do, but it tries to save you getting out of the ellipse, and it does very nicely, okay? So question comes up is like, how bad it would have been if the CBF was not there? These guys had a lot of fun, right? But what if I turn off the system? Well, they didn't do that. They wanted to keep themselves safe. But what they did after they did the experiment, and this is one of those experiments you can see, is what happened is that they said, oh, what if I would give the driver input? And in this case, that's a simulator, right? So that blue trajectory is the simulated trajectory. The CBF is kept them there. If the driver would actually give that input, which he was giving, it would shoot away and then would spin around, okay? So it really works very nicely. Now, of course, we haven't solved all the problems. I basically showed you sub-problems of how to keep in the lane, how to also keep the vehicle not spinning out. We have to put this together, right? After all, we're supposed to stay on the road and then also want to push your vehicle to the limit. But that's probably another control seminar, maybe a few years from now, okay? So before we go away, there are 2 shameless advertisements I want to do. So one of them is that there's a new book. There's no drifting in it, unfortunately, but there's a lot of cool stuff. So if you're interested in it, you can download it. Hopefully you're gonna like it. And the second thing, that's your homework. So we have the IB conference here. If you work on vehicles, please submit. You still have about 6 weeks still, right? You can even write multiple papers in that time. So please submit. This will be here in Detroit. And then we really want to show how cool stuff we can do here in Michigan. So with that, thank you very much for your attention.
Have time for questions?
Nice talking. So I'm interested in the part of your talk dealing with dynamic extension. Okay, so you're basically saying that you don't control U, you actually control U dot, so U dot becomes your input, and then so the U's become states. What would happen if you made your control barrier function include those U states themselves? Is there a possibility that you just can't get feasible barrier functions that work in that case? Because I'm thinking of like examples where you can't get the trajectory to stay inside the barrier while also keeping your control inputs bounded.
Yeah, so I think there are at least 2 questions hidden in this question. I'm going to try to answer them separately, okay? So the first one is that, let's say I have a system and then I make a dynamic extension. If I had a CBF which worked without the dynamics extension, maybe it was a control affine system, so I could design it. Will it work when I do the dynamics extension? And the answer is, by default, no. Okay, there is no guarantee for that. And there is a lot of research kind of toward this area. So what is basically happening is that, when you do the dynamic extension, your state space becomes larger dimensional, right? So imagine that we had this ellipse in, let's say, a 2-dimensional case, and I make it 3D, that becomes a pipe, right? And most of the time, you can't make that pipe control invariant, okay? You have to chop off basically parts of it. So this higher order CBF is one way to chop off some parts, essentially. So imagine if you're very close to the lane boundary, but your steering is in the wrong direction, you won't be able to maintain safety. So I think this is a major problem, and this relates to the fact that we had this condition where the nabla H times G, right? So that sometimes was 0. When that happens, you have no control authority. And the challenge is that maybe you designed it nicely for the lower dimensional system, you go higher dimension and everything goes crazy, right? So this is a very difficult thing to do. There's a second question you ask, and this is related, is that, what about the control being bounded, right? So as a matter of fact, in these simple cases, I always neglected that. To be honest, in terms of the steering, we typically are okay because we have a lot of leverage there. In terms of torque, of course, we are always limited. That's another issue because CBFs, well, they are myopic, right? They don't see into the future. So there is a lot of effort on that as well, how to include it. In some cases, actually, we can do it. So we can do even things like, for simple scenarios, that we have a valid CBF for lower dimension, and we can satisfy some control bounds, and then we can extend it into a higher dimension, and it still works. And so it means it's still a valid CBF, and also the bounds, we call it feasible, right? So because the bounds are also kept. But there is no silver bullet. We don't have a general solution yet, and there are many different directions we are actually pushing to get it more kind of a better tool set, basically. I hope I answered the questions.
Yeah.
Other questions?
I was curious about your thought of like where the research in terms of deploying autonomous vehicle in the city in terms of the safe way, where the next research problem would be. Is it like a multi-agent type of problem because we're interacting with other road user, or that's not actually a control problem, but more like system design problem? I was curious about your thought on this.
Yeah, this is of course, in some sense, the million-dollar question, right? Because if these companies know how to do it, then it would be easy. We would see more and more deployments happening. So I think maybe the right question to ask is not necessarily like, what are all the problems to do this? I think there are many. think maybe the right question to is ask as a control engineer, what can you do to help, right? Because we don't have all the tools, right? So we have a certain toolkit, which is really fun to play with, and I think it's very powerful, but it's not going to solve all the problems. So my view is that many of these companies, they want performance, and what they typically get that performance from is A, trial and error, B, automatized trial and error, which is basically machine learning, right? Or artificial intelligence. They are really pushing into that direction. I don't think we can keep up with that, right? So just Professor Komorowski told me this story that he asked a student design a controller for a quadcopter, and then he got it in 15 minutes from ChatGPT, and it worked, right? How long would it take for you to do that, right? I think that's a big challenge for our community. I actually don't think we should try. This is a game which is kind of gone. But let me ask, was that controller safe? No one knows, right? So how are we going to make sure that it's safe? Okay, it actually has some performance bounds. So safety is actually one performance bound. I think that's what we are good at, right? If I give you a system and I give you some input bounds and I ask you some output bounds, you're a good person to talk to. I think this community should really think about these kind of problems to solve. And that's where all the toolkits come in. You need modeling, you need estimation, you need control design, you need to know what is an invariant set, all these kind of things which our community is really good at. I think it becomes very useful. You just have to figure out how you're going to put it on the top of these crazy complicated things, right? Google is not going to change its AI because we come in and say something. As a matter of fact, this is how CBF was born, according to Aaron Ames. Okay, so I'm quoting him. He said that they came up with this beautiful theory, and actually it was all Lyapunov, right? Everything was nice and so on. And they went to Toyota and they told Toyota, is like, what's the chance that you take your controller from your vehicle, we're going to delete it, and we're going to put our controller there? And the Toyota said, the chance for that is absolutely zero. That's not going to happen. That controller has been there for 25 years and has been validated, things like that. And then they asked the question, is like, is it possible that we would modify that signal in a minimally invasive fashion, and then we can do that? And Toyota said, maybe. Well, apparently they are into it, right? So I really think that the garden's role is what we can play, and that's where our toolkit is used for. The underlying algorithms which they are running, they are getting basically out of control, right? There's no way we can trace them, how many parameters are in those networks. And I think that's just my answer. It's probably not the answer to your question straight, but I think that's hopefully still useful for you.
I have one question, if we have the time. Yeah, we have 2 minutes, at least up to 4:30. So you in the first part of the talk, right? I mean, you said essentially, okay, due to model limitations, at least my understanding, right? I mean, I can have my vehicle, follow and stay within the 2 lines, artificial lines, when my vehicle is up to 10 meters per second.
Right.
So I'm wondering, what is the limit to that? So you have now better models, right? I mean, you can also start thinking about, side sleeve, whatsoever the paramorphosis, how it's called, the plasticity of the tires. So what is currently the limit, essentially, in terms of how fast the vehicle can go, and what is missing from a control barrier function integration perspective, so we can actually reach, the 80 miles per hour, right?
Yeah. So I think we're not there yet, for sure. It's not there at 80. I think we are currently operating in this 10, 15 meter per second where we are kind of comfortable. I think what we are working on now is trying to extend these kind of simple designs which we have on the kind of 2-state models to these like 6-state models. It turns out to be much harder than we thought, but there is hope. I think we are very close with that. I think once we have that, then we can say you can go as fast as you want. Of course, there's still going to be model fidelity and so on. But I think this kind of, the big barrier is now that the kinematic model have these non-harmonic constraints, and we have to abolish them, and we have to kind of nurture the new dynamics. And we are working on it. I think it's a solvable problem, and that allow you to have it higher.
It's kind of a trade-off of how much fast you can use your, a trade-off of how high fidelity you can be, which compromises, I mean.
Right. And of course, you can always have robustification there, right? So I didn't talk about it today.
Yeah.
You can robustify for model parameters and model errors, matched and unmatched and so on. So that's actually possible. But first, we want to have it for a kind of tired model where it works, right? I think once we have that, then we are in the game.
Thank you, yeah, thank you.
Well, it looks like we are out of time, so if there are additional questions, maybe ask the speaker directly after the seminar. But with that, let's close and let's thank the speaker one more time.